All right, today we're looking at right triangles a little bit more in depth, and we're doing a little mixed triangle review as well. So just to remind you from the first semester, we did a proof of the Pythagorean Theorem. So we should know what the Pythagorean Theorem is. It's a squared plus b squared equals c squared. Let me write that up at the top. So a squared plus b squared equals c squared, Pythagorean Theorem. So we did it as a visual proof. We did some paper folding. So here is the visual from last semester. We folded using this technique. So we folded, we made essentially 32 of these congruent right triangles. Right here I can see 1, 2, 3, 4, and so forth. Right, we folded and made those right triangles. And then we focused here. If we call this side A, this side B, this side C. The two legs are A and B, the hypotenuse is C. We can see that if we make a square, so this side, if we build it into a square, we can see that this space, A squared, plus B squared, is equivalent to C squared over here. We see 2 of those right triangles, another 2 of those right triangles, and here we saw 4 of them. So we see that the area here plus here is equal to the total area here. So a squared plus b squared equals c squared. Again, that's from first semester. We did a visual proof with paper folding. All right, so here I'm showing you another way of doing a visual proof. So proving the Pythagorean theorem without words. So the way that we're going to do this is we're going to visualize area in 2 different ways. So the first way we're going to visualize it is looking at this whole square. So I can see that this square right here, this side, is a plus b, and then this side is the same, a plus b. If you wrote it as b plus a, no problem, it is the same thing. So I can visualize it as the area of a square. Okay, but I could also visualize it as the sum of all of the smaller parts. So if I'm looking at my smaller parts, I see, oh, I have these 4 right triangles and this one square that's in the middle. So I'm just going to say area as sum of the smaller parts. Okay, so area in 2 ways. So if I look at area of a square, I know that each side is the same. So base times height, it would be the same value times itself. So I can say that it's a side squared, or a plus b squared. So if I'm multiplying out a binomial squared, that's the same thing as writing that as a plus b times a plus b. Okay, and then when I FOIL that out, I have a squared plus ab plus ab plus b squared. So here, those 2 terms in the middle, those are like terms, right? They're both a times b, so we have 2 of them. So I have a squared plus 2ab plus b squared. So if I express the area of this figure as the area of a square, right? A plus b times a plus b. Okay, but I could also tackle it as the sum of the smaller parts, and those smaller parts are these 4 right triangles and that one smaller square in the middle. Okay, so if I have each of these triangles, let's say I look at this one, they all have legs of A and B. So that's the base and the height. So if I think about it, I have 4 of them. Each one has an area of 1/2 base times height, because a triangle will always be half of what it would look like as a rectangle. So rectangle always splits into two congruent triangles. All right, so here we're saying half base times height. Base and height are A and B. Okay, and then my square here, all of the sides are C, so C times C is C squared. So now if I simplify here, 4 times 1/2 is 2, so 2AB plus C squared. So I've looked at my shape here, and I've calculated its area in two ways. Area of the big square, area as the sum of the smaller parts. So these are equivalent statements. Let's join them together next. So A squared plus 2AB plus B squared is equal to 2AB plus C squared. Okay, now we see that if I subtract away the 2AB from the left, it's going to subtract away from the right as well, and it's going to leave us with the Pythagorean theorem. So A squared plus B squared equals C squared. So it's another way of confirming the Pythagorean theorem. A squared plus B squared equals C squared. Okay, next what I'm showing you is a partial list of common Pythagorean triples. So all that means is that these are common sides of right triangles. The most common one is that 3, 4, 5. Okay, and one thing I just want to point out to you, let's say that I draw a 3, 4, 5. 3, 4, 5. Right, we can recognize that 3 squared plus 4 squared would equal 5 squared. 9 plus 16 equals 25, right? That is a true statement. So if I have this common triple, I can actually build more common triples based on this initial one. So if I double all the sides, for example, that could be a new triple. If I triple all the sides, that could be a new triple as well. So let's look at it. If I doubled all the sides, right, it's going to create for me a similar right triangle because all of my sides will have the same ratio, right? We're just doubling all the sides. So here I would have 8, here I would have 6, and here I would have 10. So I can create more Pythagorean triples based on this initial one, right? If I double all the sides, if I triple, if I quadruple, I can apply any multiplier I want and make a new right triangle. So over here, if I just double check that, is 6 squared plus 8 squared equal to 10 squared? Is 36 plus 64 equal to 100? Yes. So I'm just confirming that it's still a correct statement. All right, so next we're going to actually use the Pythagorean theorem to solve for x. So I've given us 4 different right triangles, and we could be solving for a leg or for a hypotenuse. So my legs are A and B, my hypotenuse is C. It really doesn't matter in which place I put the missing leg. I could call it A, I could call it B, it does not really matter. All right, so if I'm looking at A, I can see, oh, I'm solving for a missing leg right here. And when I look at this, let me scroll down for just a moment to here. If I look at this triangle, what I might see is, oh, ooh, it's a common triple. So you're going to notice that I've tucked in quite a few of the common triples into these problems. So if you can see that right away, you could actually stop and say, oh, I can see that Miss Crystal gave us a common triple. I recognize that as a 20, 21, 29. So x has to be the 21. But maybe you didn't see that, so you kept going and you used Pythagorean theorem. That's fine. So x squared plus 20 squared equals 29 squared. I can still solve it this way, that's fine. I'm just giving you a few built-in shortcuts. If you can see a common triple, one of these 5, or a multiple of one of these 5, it just saves you some time. Okay, so let's say that I keep going. So now I have x squared plus 400 equals 841. Okay, and I'm going to take away the 400. So x squared equals 441. Okay, and then if I solve by taking the square root, okay, 441 is a perfect square. I would get plus or minus the square root of 21. And now that I'm seeing that x represents a side, it has to be only the positive, so it has to be 21, right? So again, if you can recognize a common triple, excellent, there's a shortcut built in. And if you don't, you can still go back to Pythagorean theorem, right? Either leg could be A and B. The hypotenuse, that longest side that's opposite the right angle, that has to be the C. All right, next one over here. Here I see I have a leg of 10, a leg of 24, and a hypotenuse of x. So if I look at all of my common triples here, do I recognize a pattern? And I can see on that second one, yes, I can see a pattern. If I think of this as 5 times 2, and this is 12 times 2, then this would be 13 times 2. I can see another common triple. So a 5, 12, 13, but times 2. So 10, 24, and 26. I can see that x is 26. But again, I know that some of you may not see that, so you would then use Pythagorean theorem. So here I have 10 squared plus 24 squared equals x squared, because here I'm solving for a hypotenuse. Over here I was solving for a leg. So now keep going. I have 100 plus 576 equals x squared. X squared equals 676. Take the square root. 676 is a perfect square. It will give us plus or minus 26. And again, algebraically, we get the two answers, but geometrically, x is a side, x has to be positive, only the 26. So here are two examples of a common triple built in. Here, just a common triple, and here it was a multiple of a common triple. Every side got doubled. So if you can recognize those patterns, it gives you a shortcut. If you can't, you're just using Pythagorean theorem. Okay, these two at the bottom, these are actually both special right triangles. Okay, this first one is an isosceles right triangle, or a 45, 45, 90. Okay, and we're going to deal with that pattern pretty soon. So let's say that I don't recognize that, and I'm just solving using Pythagorean theorem, right? I have two legs, they're both the same. So I have x squared plus x squared equals 6 squared. So I have 2x squareds equals 36, right? I'm solving for x. I divide both sides by 2. X squared equals 18. Okay, solve by taking the square root. 18 is 9 times 2 with a pair of 3's. So I'm going to get that x is equal to plus or minus 3 root 2, but it has to be the positive. It represents the side, 3 root 2. So both of those legs are 3 root 2. And like I said, this is actually a special right triangle. This is a 45, 45, 90 triangle. That's where we're headed. We're going to start talking about the special right triangles after this lecture. So here, the pattern that I'm hopeful that you're able to recognize, let me just write that this is a 45, 45, 90 triangle. These angles would have to be the same. They're splitting the remaining 90 degrees, 45 and 45. Or we could call it isosceles and right. Okay, either way, it's one of our two special right triangles. And the pattern that we should recognize is that the two legs will be the same, and the hypotenuse is a leg times the square root of 2. So if I go backwards and I say, okay, well, if these are both 3 root 2, and I multiply 3 root 2 by root 2, that's saying 3 times 2, and that would get me back to 6. So I'm just pointing out a pattern that we're going to talk about more next week. All right, this next one is actually the other special right triangle. It's a 30, 60, 90. And I only know that because, again, I can recognize a pattern. My short leg is x, opposite my smallest angle. My larger leg is x times the square root of 3, and my hypotenuse is 2x. So my sides will always be in that sequence. I'll have an x root 3, and then a 2x. So here, let's say I didn't notice the pattern, so I just want to solve using Pythagorean theorem. I can say that 5 squared plus 5 root 3 as a quantity squared equals x squared, right? I'm solving for the hypotenuse. So 5 squared is 25. 5 root 3 squared is like saying 5 times 3, so 75 equals x squared. So x squared equals 100. Solve by taking the square root. X could be plus or minus 10, but we know it has to be the positive 10. Right? It has to be the positive 10 because it represents a side. So again, let me talk back this pattern, the 30, 60, 90, right? I'm foreshadowing where we're headed. So my short leg is the x. So here's my short leg, 5. And then I take that short leg, I multiply by root 3, there's my longer leg, okay? And then 2x is my hypotenuse. So my hypotenuse here is 2 times that short leg. 5 times 2 gets me 10. That's what I got right here. Okay, so again, I'm just foreshadowing where we're headed. We can still solve for these missing sides using the Pythagorean theorem, but it's all about finding little shortcuts, and we'll talk about these shortcuts a little bit more in depth next week. All right, let's flip over and do the back. All right, so for 3 and 4, I'm having you find area. Area for a triangle, we know is 1/2 the base times the height. So find the area of the isosceles triangle. So an isosceles triangle splits right down the middle into 2 congruent right triangles. So that means that our base right here's the 2 legs, here's our base. This is the vertex angle, these are the base angles. Right? That base is being bisected. It's split into 2 congruent parts. So these 2 segments would be 6 and 6. So I need to figure out what is the height. What's the height right there? What is the measure of that perpendicular segment that connects vertex to base? So find the height. So I'm looking at one of the 2 congruent right triangles, and I need to solve for a missing height. I need to figure out what's the length of this leg. So using Pythagorean theorem, 6 squared plus my height squared, I'll just label that as h, is equal to 8 squared. So 36 plus my height squared equals 64. Take away the 36. My height squared would be 28. Solve by taking the square root. So 28 is 4 times 7. So h would be plus or minus 2 root 7. Okay, but only the positive. The height has to be positive. So 2 root 7. Okay, so I have my height has a measure of 2 root 7. So now I want area. Area half base times height. So here is my base, and here is my height. So half of 12 times 2 root 7. So half of 12 is 6. 6 times 2, we're back to 12. And then root 7, that is my area. So 12 root 7 units squared. Okay, example 4. Remember that an equilateral triangle is still isosceles, so it also splits right down the middle and makes 2 congruent right triangles. But I can further classify when it's equilateral. All of these angles are 60, so if I split this one in half, these would both be 30-degree measures. So I can see that here it splits into 2 congruent right triangles, but they're actually 30, 60, 90 triangles as well. So again, this side that's 8 splits into 4 and 4, and I have to find my height. So I'm going to have to use Pythagorean theorem again until I start to get better at recognizing that 30, 60, 90 pattern. So here I have 4 squared plus my height squared equals 8 squared. So 16 plus the height squared equals 64. Take away the 16. Height squared is 48. Solve by taking the square root. So 48 is 16 times 3, so 4 root 3, plus or minus 4 root 3. Okay, so algebraically I get the two solutions, but geometrically I can only have the positive, so 4 root 3. So my height, 4 root 3. Area, half, base times height. So half of 8 times 4 root 3. So 4 times 4 is 16, and then root 3 units squared. Okay, so again, just to back up and talk about that 30, 60, 90 pattern again, right? I pointed it out to you on the flip side. So here the short leg is x, right? Here that's 4. That long leg would be the x times the square root of 3. So if this is 4 root 3. That makes sense. I still solved it using Pythagorean theorem, and the hypotenuse is 2 times that short leg, 2 times x. All right, example 5, throwback to last semester. So what range of values can a triangle with the following sides have for its third side? So to remind you of how to visualize, I used lots of strips of paper last semester. I'm going to do the same this semester. So here, if this is 6 and this is 4, tiny little strips of paper. Okay, so if I'm looking at a larger side of 6 and a shorter side of 4, what range of values can that third side have? Well, if I put my finger here, hold that kind of tight, make that the vertex of my angle right here, I can see, well, it has to be more than 2, because at 2, it would be a straight pathway. So if I open it just a little bit like that, right here where my finger is, that angle measure is increasing from 0. So it's getting a little bit bigger, and this side could be a little bit more than 2. Could be 2.3, could be 2.5, could be 3, right? I can open this up all the way until I get to this other extreme. And at any point from that path, the angle where my finger is right here is increasing from 0 to 180. So right here is 0 degrees, right? This can't be exactly 2. It could be a little bit more than 2 like that missing side. And then I can still make a third side of a triangle anywhere until I get to this other extreme right over here, which would be the sum. So that third side has to be more than the difference, but less than the sum of the two known sides. Let me pull that away. Okay, so if I write that down, C has to be greater than A minus B. Think of that as my difference, but also less than the sum of the two known sides. So I showed you with my strips of paper, C has to be more than 6 minus 4, has to be more than 2, but at the same time, C has to be less than 6 plus 4, which is 10. So that third side has to be more than 2, but less than 10. So this right here is inequality notation. If you want to write it in interval notation, you could say 2 to 10, just like so. That would be fine also. Okay, if you like drawing it out, like how I showed you with the paper, the two extremes, here we go. This would be 6, this would be 4, this would be 6, this would be 4. So I'm just showing you that that third side right here, right, has to be a little bit more than 2, a little less than 10, or somewhere in between. All right, I think it froze for a second. Let's see if it will unfreeze, and then I will pick up that second part. Let's see. Well, I think we froze. Okay. Well, I'll stop and then I'll pick up on that example.